Professor Dave here. Let's graph some trig functions.
He knows a lot about all kinds of stuff. Professor Dave explains.
We've just spent some time learning about the 6 trigonometric functions, as well as how they relate to one another, and the unit circle. Just like any other function, we will want to be able to graph them, but there are some interesting things that we can point out about these functions first. First, let's talk about the domain and range of the functions. Looking back at the unit circle, we know that each point has the coordinates cosine theta, sine theta. So looking first at sine theta, the domain of this function is the set of all the angles we could plug into this function, and the range of the function is all the possible values for sine theta. This means that the domain of sine theta is all real numbers, since we could plug in any angle. It could be greater than 2 pi radians. We just end up going around and around indefinitely as we approach infinity. And we could also have negative angles. We just go the other way. But the range of the function is -1 to 1 inclusive. Sine theta can only have values within this interval, as we can clearly see from the unit circle, as the y values of all of these points are somewhere in between -1 and 1. The same goes for cosine theta. We could plug in any angle, but if we look at the x values of these points, they always fall between -1 and 1. So both sine and cosine will have a domain of all real numbers and a range of -1 to 1. Tangent is different because that's sine over cosine, and as cosine gets very close to 0 in either direction, the function gets very big, approaching infinity. So the range of tangent theta will be all real numbers. The domain is almost all real numbers, but we can't evaluate tangent when cosine is 0, because anything over 0 is undefined. Cosine is 0 at half pi and 3/2 pi, so the domain of tangent theta is all real numbers except half pi plus or minus multiples of pi. The other thing we want to understand about these trig functions is that they are periodic. Their values repeat over and over again as we go through each period of the function. The period of these functions is 2 pi radians, because after 2 pi radians, we are back to where we started and all the values repeat. In other words, the sine of x plus 2 pi is the same as the sine of x. The same goes for cosine. Let's go ahead and graph the sine and cosine functions now so we can see exactly what they look like. Let's bring up the coordinate plane and also the unit circle. Looking at the y coordinates of these points, we can start to plot the graph of y equals sine x, going in multiples of pi over 6. When x is 0, y is 0. When x is pi over 6, y is 1/2. When x is pi over 3, y is √3 over 2. When x is half pi, y is 1. Then, as we move through quadrant 2 of the unit circle, the sine values start to go back down until we get to x equals pi, where y is again 0. Now, as we enter quadrant 3, we start to get negative values for the y-coordinate, and thus negative values for sine x. These will be the same values as the first 2 quadrants, just negative, until we get to -1. And then, moving through the 4th quadrant, we get back to 0. So there is the graph of y equals sine x for one period of the function. Once we get to 2 pi radians, it's the same as being at 0, and when we enter another period of the function, all of the values will repeat. That's what makes this a periodic function. If we graph multiple periods of the function, it looks like this, and we can clearly see its cyclical nature. How can we manipulate this function? Well, we can apply any of the transformations we learned in algebra. If we put a coefficient here, that will stretch or shrink the function, which will change the amplitude of the function. y equals 2 sine x will look the same, except that all the values are doubled, so we are cycling between 2 and negative 2. If the coefficient is negative, it reflects everything across the x-axis, which looks like this. In this way, for any function in the form y equals a sine x, the amplitude will be equal to the absolute value of a. If instead there is a coefficient operating on x, that would be a horizontal stretch, as y equals sine of 2x would mean that the function will rise and fall at twice the normal rate. This would mean that the period of this function is pi instead of 2 pi, and in fact, for any function in the form of y equals a sine bx, the period is 2 pi over b. Lastly, we can have vertical or horizontal shifts. If we have a term that is being added to the function, that's a vertical shift, just like we saw with parabolas. Y equals sine x plus 1 will just shift everything up 1. If instead we have some number inside the function, like y equals sine of the quantity x plus half pi, this whole thing will shift half pi to the left. As it happens, we have just generated the graph for y equals cosine x. This will make sense if we refer to the unit circle again and see that the cosine of 0 is 1. That means the function must start up here. Then the cosine decreases until we get to 0 at half pi, then goes towards negative 1 at pi, then it's back to 0 at 3/2 pi, and then up to 1 at 2 pi, after which things repeat. So the graphs for sine and cosine are extremely similar. They are just slightly shifted, and all of the transformations we used for sine x will apply to cosine as well. Let's use what we've just learned to graph one period of 4 sine of the quantity 2x minus 2/3 pi. First, let's find the amplitude. We can get that from this number here, which is 4. So the function will move between negative 4 and 4. Then let's find the period. That will be 2 pi over this term, so the period will be equal to pi. Then we find the phased shift. This term would mean that the whole thing is shifted 2/3 pi to the right from the origin, but we have to divide that by this number since this is causing things to contract, so that leaves us with pi over 3. So the period will start at 1/3 pi and end at 4/3 pi, going up to 4 and then down to negative 4 before coming back to 0. We can find the x-coordinates of these key points as well. We just have to split the period up into 4 parts. That gives us a 1/4 pi, and we just add 1/4 pi successively, starting with 1/3 pi to get all the x-coordinates. To do that, we need a common denominator, which will be 12. And then we combine and reduce, using the rules we already learned for adding fractions. Before we move on from this subject, let's just quickly look at the graphs of the other trig functions so that we know what they look like. Tangent looks quite a bit different because the range is no longer negative 1 to 1, like for sine and cosine. Instead, this function approaches positive and negative infinity as cosine values approach 0, and when cosine is 0, tangent is undefined, so we have a series of vertical asymptotes. Here is the graph for y equals tangent x. It has a period of pi because tangent values from quadrant 1, where sine and cosine are both positive, come back again in quadrant 3, where sine and cosine are both negative. Likewise, tangent values in quadrant 2, which are positive over negative, come back in quadrant 4, where it's negative over positive. This function can be transformed in all the same ways that we saw for sine and cosine. Cotangent will be similar, but as it is the reciprocal of tangent, it's a little different, falling to the right instead of rising, and shifted slightly since the x values that originally generated asymptotes will now generate y values of 0, as 1 over infinity is 0, and the points that originally had y values of 0 will now contain asymptotes, as 1 over 0 is undefined. Cosecant and secant will also look a little funny, as all the points where the sine and cosine equal 0 will now be asymptotes for their reciprocal functions, again because 1 over 0 is undefined. The transformations for all these graphs are exactly what you would expect, so having gone over this already, let's check comprehension. Thanks for watching, guys. Subscribe to my